We better start, and
Yeah.
I'm sure more people will trickle in as we go. So hi everybody, and welcome to our seminar. Today we have Jay Quade as our speaker, and Yuda Enzel will present him. So take it away, Yuda.
Okay, it's great.
Hey, Yuda.
Hi, Jay.
Hey, good to see you.
Most of the audience here actually met Jay when he was here.
Great.
But I'll just summarize his history, scientific history, very fast. He worked in master physics he did in the University of Arizona. He worked on the groundwater discharge deposit that we never stopped since working on them. Then he moved to Utah and he did the geochemistry with then Uri Serling on the geochemistry of stable isotope of oxygen isotope in soil carbonates, so on. Then he was in ANU in Canberra. And then he joined University of Arizona and never stopped shifting all around the world. North and South America, Asia, East Africa, and producing benchmark papers. And for them, he received amazing list of awards, including the Day Medal of GSA, which is given for outstanding distinction in contributing to geological knowledge through application of physics and chemistry to the solution of geologic problems. He received the Farouk El-Baz Award and is a fellow of the Geological Society of America, AGU, Geochemical Society. He received a fellowship from the Japan Society for Promotion of Science. And 7 years ago, he came to us as the lecturer of the Bento lecture, had an impression, and a few years later, he joined us as a Lady Davis Fellow and a visiting professor, where he worked with some of our students. And I think today we're going to hear even one collaboration that still continue with our students. Today we'll talk on Central Andean Megaflood record for the last 25,000 years from Salinas del Bebedero, Argentina. Jay, the floor is yours.
Okay, can everybody see that? All set? Okay, good. Thanks, Yehuda. And boy, it's good to be back amongst my Israeli colleagues and friends. I think constantly about my time in Israel back in 2016, and I would love to do it again, and certainly will. But in the meantime, today what I want to talk about is work I've been doing in South America in a place called Salinas del Bebedero in sort of central Argentina, in a little studied part of South America. It was part of the reason I wanted to work in this area. And what attracted me to the region, besides that there's very little known about it, were some remarkable deposits, a remarkable story, actually. And this is the first time I've ever given this talk from the Salinas del Bebedero. It's one of those sort of situations where you're just exploring around. You don't know exactly what you're doing. You're just looking for interesting stuff. And boy, this basin is really unusual. I'm still trying to understand it. One of the really interesting and unusual features of it is first of all, just the appearance of the deposits. This is a typical sort of scene. There's many of these, and I'll show you on a map where all the stuff is in a second, but just to give you a taste of what it looks, we just get out in the ground and walk around. And you see what we see on the photo here is this odd sort of, how do I describe it? A kind of draping of deposits, younger deposits over the top of older deposits. And when I first saw it, I'd never seen anything like that, that odd sort of hummocky draping. And let me draw a line through it. So sort of my sketch of where it is. And you can trace this kind of draped, it's like a wet blanket laid down on the landscape and filling in all the depressions. Some places as deep as 3.5 meters. And you can trace these things for kilometers. They're very, very widespread. Well, I now think they're, as the title implies, they're basically flood deposits. And the question we're addressing here is sort of what does the record mean? If they are floods, what does that mean? Where do they come from? What's the age? Various questions. So let me list them out here. Things I want to cover today. So are these flood deposits? The Argentinians have worked here a little bit, but not very much. And they've suggested that they could be flood deposits. If so, how old are they? This is something I really worked hard at, being at the radiocarbon lab at Arizona, having access to a lot of analyses. Where do the floods come from? It's a very small catchment. It's out in the middle of the Argentinian desert. It's not clear at all. Like where the heck, where does the mud come from? Where does all the water come from? Because these are quite extensive. They cover many, many square kilometers. How big were the floods? And what do they tell us about the hydrology of the region? And whatever we conclude about the record, it's important in filling a major geographic gap in South America. At 33 degrees south, there's not many records that have been worked on. Okay, so let's we'll come back more to the physical sedimentology and this, this interesting hummocky appearance to everything. I'm always thinking about bigger questions, and the bigger question I'm addressing in South America, I've worked there for years, is could perhaps this record of flooding at Bebedero be somehow related to the expansion of the tropics? There's a lot of evidence. What we're looking at Bebedero is flooding, large-scale flooding of the desert in an area that normally doesn't flood. And there's my favorite example of that elsewhere in South America of large-scale flooding over the last 25,000 years is the overflow of Lake Titicaca, another place I've worked. The flooding that resulted in creation of a mega lake, it's referred to as Tauca, that covered all of southern Bolivia. It was so big. I'm standing on the shoreline. That's a tufa head right there. And the background is where the lake was. It's gone now. So it was several hundred meters deep, and it was 2.5 times the size of Israel. This is just this monstrous lake that flooded major desert areas of South America. So naturally, a question for me is, how does Bebedero relate to the chronology here? And I'll show you on a map where these are. We'll get everything interconnected. The story from Bolivia, our general thinking is that the lakes developed there because of southward expansion of the tropics, southward not so much northward, but southward growth of the tropics between about 17.85 and 14.5 Ka during Heinrich Stadial 1, which I'll talk more about as we go on. And I think that all of this is Bebedero, Tauca, and other well-known places is all part of a much larger story of a major hydrologic perturbation of deserts, the largest such perturbation in the last 100,000 years in the Americas, and not just South America, but also in North America. But the question for today is that did this perturbation reach as far south as Laguna or Salinas del Bebedero, which is at 33 degrees south? It's kind of an unknown, poorly documented zone of South America. Yeah, and that's me standing on the shoreline. Isn't that amazing? Look at that. That thing stretches for 2.5 times the size of Israel. Biggest mega lake in the Americas outside of, or sort of equivalent to the size of Lake Bonneville in North America. Okay, so let's do some locations here. First of all, in this little inset, there's the Bebedero basin right there, or actually the adjacent drainage. So it's in central. You can see here at about 33 degrees south, sort of central mid latitudes of South America. It's bordered on the west by the Andes, but it's a long ways away, and this is a 100-kilometer scale, so Bebedero is over 200 kilometers away from the Andes. This is the catchment area of the Rio Desaguadero River. The Rio Desaguadero is a large river that drains this whole sector of the Andes from 28 to 34 degrees south, flows past the big city of Mendoza, drains Mount Aconcagua, which is the largest peak in the Andes. And there's a whole series of rivers that join to make the Desaguadero. But what's interesting is the Desaguadero, doesn't flow into, but flows right past the Bebedero Basin. There's a lot of structural activity out here in the San Luis Basin. And actually, the Bebedero Basin is a little isolated structural basin that is not reached by the Rio Desaguadero. Here's a blow up of it. There's the Rio Desaguadero flowing right on by. And during normal flow stages, the river won't reach, it flows right out to the Atlantic. But during flood stage, there's a low sill that divides the two basins, and it's possible for the river to overtop that sill and flood into the basin. So that's really interesting. I haven't come across that many situations like this where Normal flow, normal discharge is not reflected in a record, but only floods are. Only large discharge along the Rio de Secadero, large enough to get over the sill, which is anywhere from 3 to 5 meters high, can reach into the basin. So this is it's a flood recorder basin, but not just the small floods of the big floods, because they have to travel presumably 200 kilometers from the Andes, and then they have to be big enough to reach up over that sill and reach into this basin right here, Laguna del Bebedero. Okay, so that's a basic picture. And Elad Dente, who's is my co-presenter today, he's going to talk a lot more about the magnitudes of floods and so forth. And but he was instrumental in identifying the fact that some of this ground here is almost certainly deltaic flood deposits. This white zone in here, because most of the area is covered with relic Pleistocene dunes, but right in this area, there's a lot of evidence of big flood deposits, big delta, and that the flow just basically went like that during high flood stages. Okay, so here's a geologic map here, a geologic sketch map, and then the same thing I was showing before. This map, let's see, where depicted on here in brown is the paleosplay of the point here where the river would overtop during the flood stage, would overtop the sill and flood into the basin. The light blue is the high shoreline. It's this outline right here. It's the highest shoreline at about 410 meters. At maximum depth, the lake was about 30 meters deep, so it's not all that deep. And then there's a whole series of inset shorelines reaching down to the modern playa in the middle, and a salt mine in the north. Argentina gets most of its table salt actually scraped up off the surface of this playa. But there's the shorelines, and the high shoreline is defined by this light blue. It stands at 410 meters. And at the high shoreline at 410 meters, actually what happens is that the waters flood into the basin, and they fill the basin, and then they flow back out. There's no place else to go. So they'll go back into the Rio de Salvadero. So that's what happens in the high shoreline. And then but there's other intermediate shorelines present there too. And then dark blue is the modern playa. So I'm going to walk you through a few exposures just to give you a sense of what these deposits look like. And we're going to start with a high shoreline over in here. We'll look at some exposures of that. And then finally, we'll go down in this vicinity out along Bebedero Creek, where most of the exposures, natural exposures are. There's incidentally a tremendous story there, and I just scratched the surface. I spent 2 field seasons out there, a total of about a month and a half, and man, there's a lot more work to do. I feel like I've just got the basic outline of what was going on. But I'll take you to visit some exposures along Bebedero Creek that show the repeated or cyclical pattern of flooding, okay? So first stop is, or when we look at the stratigraphies, we're going to go to the high shoreline, and then we're going to look at some other places, okay? So first, a little bit about the nuts and bolts. I did a total of 22 really detailed stratigraphic sections, identified 12 what I call flood layers, and I've designated them kind of cryptically the glacial maximum events. E stands for events, so glacial maximum events, there's 2 of those. Late glacial event, there's 6 of those, and late Holocene events, LHE, there's 4 events, for a total of 12, and that 12 and counting. And these are just the big events. These are the things I can see in the shoreline stratigraphy. I imagine there's many, many more events recorded if you were to actually core the playa, which I haven't done. Got a lot of dating control, lavish 55 dates on this, mostly from shell derived from 3 aquatic species. This is the capital of fossil mollusks. There are just so many, just unlimited opportunities for dating. It's Biomphalaria peregrina, Chilena parchapi, and Heliobia parchapi. Those are the 3 aquatic mollusks. The bottom line from my point of view is they're aquatic, so they're formed in the lake as a part of the flooding or the post-lake, post-flooding lake. And I generally, just straight up, I think the dating is very straightforward. You can accept the dates at face value. There's no reservoir correction. If we're right about these being floodwaters, they should be fully in equilibrium with the atmosphere, and there should be no problems from influence from groundwater. And also, we're looking at very short residence time of the lake. And this is really a key point. The lake is only 30 meters deep. And if you figure the evaporation rate is about 1.2 meters per year, the lake will only last 25 years with 1 flood event. And yet we see persistence of the lake over hundreds of years, which suggests that we've had even more flooding events than I can see in the record. But from the standpoint of radiocarbon, it means short residence time, so there's no reservoir issues. We can just take the radiocarbon dates as face value, and you end up with a very coherent story. Okay, so let's go to that high shoreline that I promised at 410 meters. This is the top fill point of the lake. This is the point where it would spill back into the Rio de Bebedero if you let it, if it got to that level. And these are the beach deposits with the capping Holocene soil. And it's kind of a not a very pretty outcrop, but when you look at it very carefully, you realize there's a whole series of sort of cemented hard grounds that are present within the sequence, interbedded with large-scale crossbeds, which represent sort of beach activity. And when you look at this outcrop actually carefully and date it carefully, this is my sort of stratigraphy that for the high shoreline berm at 410 meters. There's a whole series of dates. Most of them date between at the top at about 15,000 and at the base at 15,600. There's a few, these are calibrated ages, and there's a few ages that are 36 to 40,000 years. Those are reworked. And then if there's one problem with the dating out there is you get a fair amount of reworking, particularly those big robust shells of Chilinea parchapi, they rework easily. But if you ignore the rework dates, basically the age of the high shoreline is between 15 and 15.6. So that answers question number one. How does this relate to Tauca? It relates exactly. That's exactly the age of the high shoreline of Tauca, the big lake up in Bolivia. So it's exactly synchronous with it. And the other interesting feature of this outcrop is look at there's a succession of hard grounds, which I interpret as oscillations in the lake level. That it flooded up to this level and then receded, flooded again, receded, flooded again, and receded. Because remember, the lake will only last about 25 years or it just evaporates away. And yet we have evidence for it being up here repeatedly between 15 and 15.6. So there must have been multiple flood events, more than I can even see or count, that held it up at this level over a long period of time. So that closely spaced repetition of flooding is really interesting. How do you do that? Okay, here's another shot. Typical sort of scene out here. This is actually ecologically, it looks kind of like northern Mexico to me. It's about the same equivalent latitude. And so there's pretty light vegetation cover and you can see a lot. This is the Bebedero Formation, which contains all the Lake Quaternary flood record, and the flora of the deposits is the Rojo Salinas. I came up with these names incidentally because this area really hasn't been worked. And those are much older. You can ignore those. But if you work on an outcrop like this, so you arrive at a place like this and then spend a half a day or to a full day documenting it, you end up with a story like this. And then we're going to repeat it 22 times. But here's the Rio Salinas. And what I identified in this outcrop, I think are at least 3, probably 4 flood events. The first one being, here's this late glacial event 1, dating to about 16.5, right at the beginning of Heinrich Stadial 1. It's just right on schedule for that. There's event 2 here is this green layer. It dates to somewhere between 15.4 and 14.9. That was the high shoreline that I showed you in the previous slide. That's the same age. That's LGE2. There's an event here in this location I wasn't able to date, but it sits up right there with a break in between. There's some playa deposits in there. And then finally, a big flood event, LGE3, which dates to around 13 to 13.8, and that cut deeply into the older deposits. And so forth. That's just 3 or 4 events. And at the end of the day, if you do your homework, it's at least 12 of these things. Here's another location, just to give you a flavor of these things. So this is upstream along Bebedero Creek, and we've identified potentially 4 events from this outcrop. There's LGE3. That's this green channel deposits. A lot of the places, what that event looks like, it's a custard marl full of shell and carbonate. There's the dates on it. It's capped by another series of flood events between 12.9 and 12.3. I've lumped them into just one event, but I think there are actually several ones in here. if you really work on it. And then there's a big time gap in here, and most of the Holocene is missing. And then for the period of about 11 to 3,000 years ago, there's no flooding at all, which is really interesting. And then at the top of the sequence, we have another Holocene flood event up in here. That's a black mat, actually, and it dates to about 2,500 years ago. So the flooding comes back in the late Holocene. So that's a pretty typical sequence of, several flood events. There's the Holocene gap. One more example, a couple more examples. So, and just to remind you that this latest flooding event 2,500 years ago, it actually is mostly expressed as a black mat. It's all over the place, you can see. And then the little white specks there are just shell, which is just all over the place to date. And these white things back here are the older late glacial events. And these Holocene, the Holocene gap, I think is somewhere down in here. I'm not sure exactly on this outcrop. Okay, so then one last slide. I apologize for the quality of the photograph. It was a very rainy day, and I couldn't focus it very well. But I wanted to show you this because it's really interesting. Here's the Rojo Salinas formation, capped by that LGE3. So this is the same event as that one right there, and that one, the one in green. So this is what it looks like over most of the area. It's a yellow marl. And it's capped by, I don't know the age of this deposit here, but this is the Holocene gap right here. There's a halite right on top of this pink layer. This is a playa deposit. This is the Holocene gap. It represents about 8,000 years. And then on top of that, we're capped by some late Holocene flooding. This is event 2, and it dates to around 1400 BP. And it's very widespread, as these flood deposits are. The younger they get, the more widespread they are. The older they are, the more they get sort of cut out or buried by subsequent flooding. So that's a pretty typical deposit of the late glacial events, this Holocene gap, and then restart of flooding on a more modest scale in the late Holocene. See this pattern over and over and over again. Okay, let's put 22 sections together, detailed stratigraphy, 55 dates, and this is the picture. Picture Megaflood summary is basically there's a few events that are recorded during the full glacial, the glacial maximum events. There's a couple of them, but they're pretty subtle. What's really hits you in the face when you work out there is these late glacial flood events. This is the hydrologic maximum out there. There's at least 6 events, and I think embedded within this, for example, there's at least 3 or 4. So this is really a minimum statement of what's going on. But this is the hydrologic maximum, and it overlaps pretty much with the Heinrich Stadial 1 and the Talca High Stand up in Bolivia, and it's all the same thing. What's equally interesting, I find, is what I call the Holocene gap. As I showed in the outcrops from those 2 slides, from 11 down to less than 3, nothing happened. Nothing major reached this basin. So I don't know what was going on in the Andes, but things were shut down. Whatever was generating the floods, it was asleep during this period. And then it starts up again in the late Holocene when they have at least 4 events. And the most recent one is actually pictured in that first slide I showed you, the hummocky part. That's those capping deposits are LH4, and they're only 150 years old. So I just miss witnessing one of these things. Okay, so where do these flood deposits come from? Let's look briefly at some of the evidence, sedimentology, and then some isotopic evidence. So first of all, right back to the first slide here, and I've put this is LGE3, actually the base of the outcrop. This is the Holocene gap at the base of the outcrop, and it's capped by this late Holocene flood event 4, which is only 150 years old. And I think part of the evidence for the flooding is just the deep, hummocky, locally channelized appearance. I don't know how to get this sort of wet blanket look, except with flooding. Although maybe you guys have some experience and ideas, and I'd really be curious about what people think after the talk is over about what's going on here. Have you seen deposits like this? You guys have probably everybody in the room has looked at flood deposits. What do you think? There's isotopic evidence for where these things come from, and I'll give you the punchline right now. I think these floods are coming down out of the Andes. That's where most of the moisture is. The catchment for the Bebedero Basin itself is tiny, and so the logical candidate is the Andes. But we could test that. You could do that with strontium isotope evidence. just by measuring the isotopic composition of waters flowing down out of the Andes, of local groundwater flowing down out of the Sierra de San Luis. That's another possibility for the water. And then compare it to the isotopic composition of the fossil shell. The result is quite clear that the best match for the Bebedero fossils is not local groundwater, it's the Andes. It's not a perfect match, but it's a really close match. And so I think that's supporting evidence that the source water is coming out of the source of these floods that from which these shells precipitated here in the Bebedero basin is Andean in origin. Even stronger evidence is sediment itself. Take a look at this diagram. It's a nice illustration of what you can do with uranium lead on detrital zircons. So I sampled the Rio de Desaguadero. That's the panel on top. I sampled the sands from the Bebedero formation, and then I sampled some creeks that are flowing down to the local Sierra de San Luis. And so it's a test. It's a test of what's the source. Is it Andean, which would be on top, or is it local, which would be on the bottom? And I put Bebedero in between. And I don't have to interpret this diagram for you. I presume you can see that there's a perfect match between the Bebedero formation and the Andean sources. It looks like Andean sediment. And what really sticks out about Andean sediment and is on schedule, this is what we'd expect, is the ample population of young zircons. Because of all the young volcanism occurring in the Andes, there's no young volcanic activity in the Sierra de San Luis, the local geology, but there sure as heck is in the Andes, as everybody knows. So that young population there of zircons under 50 million years is all Andean. Now, we did get one grain down in the lower panel there of Andean zircons, but I think that's aeolian. I'm actually a little surprised there wasn't more aeolian influence there because we're right in the middle of a dune field, but it had only one Andean grain from actually sitting up in the Sierra de San Luis, and I think it was blown up there. Okay, so boy, this diagram is a smoking gun. These flood deposits, the things I've been showing, these 12 events, they come from the Andes. Okay. Natural waters, you can play this game as well. Just look at the modern waters, not fossil waters, but modern. And in blue are local Bebedero waters. They tend to be isotopically kind of heavy on the oxygen scale here, which is the x-axis. I've drawn for reference the local or the global New York water line. They're very, very similar. And you can see the Bebedero waters, most of them are kind of evaporated. And if you project them back on the local waters back onto the line, you also do that with the Rio de Desaguadero, you end up with a source water for the Rio de Desaguadero of probably around -12. After evaporation, it gets more positive, but a source water of around -12. So this is a demonstration of the obvious that the Rio de Desaguadero flows down to the Andes, but that gives us a fingerprint for what modern Andean water looks like, is around -12, -13 per mil. And it's completely distinct from Bebedero groundwater today, which is all local and much more positive. So the logical thing to do is to snap reconstructed water values from the shell onto this. And let's do that in this diagram. A little more complicated. Here's the value reconstructed waters for the using delta 18O of SMO, and this is the fossil shell. So on this is the total range of observed values from fossil shell from -12 up to about +3. And if you take those shell values and you assume formation temperatures of around between 12 and 25 degrees C, which is typical for these aquatic mollusks, then you reconstruct ancient waters. So you take that, let's take -12.5. And at a temperature of 12 degrees, you'd reconstruct an ancient water of around -14, almost -15. If you assumed a water composition of, or a water temperature of 25 degrees C, you'd get about -11. So for an average of -13 per mil, reconstructed water value based on the most negative fossil shell from the basin, which overlaps perfectly with high Andean rain and even some snow. Now, you get a whole range of values, which are also consistent with a lot of evaporation of the lake. But boy, that's not surprising. It's super easy to evaporate the lake. So the fact that you get really positive values here, no problem, that reflects evaporation. But if you take the most negative values, again, it's a smoking gun. It points right at the high Andes, and typically above about 4,000 meters. That's where you get water compositions this negative. Okay, so my sort of sub-conclusions at this point is, first of all, the chronology, which I'm going to compare to other records, but these are Andean floods. And if we lay them out against, let's do it against, compare it against Bolivian mega lakes. That was the second slide I showed. I was standing on the shoreline, and here's the age of Lake Tauca in Quade. This is the late glacial high stand of the lake, and it's just right on schedule for the main hydrologic maximum at Laguna de Bebedero. And it matches the time when there was maximum central Andean glaciation. Remember, glaciation in this region, though, is not temperature limited, it's moisture limited. This is extremely dry. So the way you grow glaciers in this region is not by depressing the temperature, it's by making it wet. And so I take the presence of a lot of Andean glaciation at this time as an indicator of very, very wet conditions, consistent with growth of mega lakes and flooding within Lake Laguna de Bebedero. It's a time of major wetness within southern Amazonia. It shows up as really negative values in Brazilian speleothems, and it's spot on for the age of Heinrich Stadial 1, H1 right there, which is defined by this record by Jared McManus from the North Atlantic. But the main point is that this thick gray line here, that's H1, and everything lines up with it, including our hydrologic maximum. Let me just remind everybody before I turn it over to Alad what the Heinrich events basically are. Particularly, let's focus on Heinrich event 1. I think most people maybe know what Heinrich events are, but let's look at them in the context of why they make South America so wet. The sequence of events leading to Heinrich event 1. It's basically a huge release of partial collapse of northern hemispheric ice sheets, but it starts with increase in summer insolation 18,000 years ago, melting and destabilization of large ice sheets in the northern hemisphere, production of a freshwater cap that shuts down thermal handling circulation in the North Atlantic, and the spread, northern hemisphere cooling and the spread of winter sea ice, which causes the southward shift in the ITCZ, and also probably of the westerlies. And this is the key thing. So South America is in the southern hemisphere, and this is the key thing from the point of view of South America, is the shift of the tropics from its usual position up around the equator southward down over Bolivia, and even apparently reaching as far south as Laguna de Bebedero. So that's basically what I think the record's telling us. And then other sort of things like increase in CO2 and upwelling and so forth, which further warm the planet. So before I turn it over to Alad, just this last slide, here's my sort of summary of, I think, what's going on. Here's Laguna Bebedero, here's Tauca right here. And they're all part of a major wetting event during the last Heinrich Stadial 1, where I think basically the subtropics normal position is up in here, but it extended as far south as Laguna de Bebedero, 33 degrees south. So these are all based on observed records. These blue dots here are areas of increased wetness during this period. And so it's the basis for drawing this red dashed line. But it's also been, this whole idea has been modeled, the impact of Heinrich stadials on rainfall belts and shifting them around, and particularly shifting the thermal equator and the hydrologic equator southward. This is an output from John Chang in 2005, an iconic paper in which, and I put in the box right over South America, his model input shows that as a result of Heinrich stadial asymmetric cooling of the north and heating of the south leads to a southward shift in the ITCZ and a wetting of central South America, the area we're talking about. So I've got a few, like 2 or 3 summary slides, but let's come back to those. And Alad, why don't you take it over?
Okay. So just stop the share.
Yeah. There you go. It's all yours.
Hi. You see it? Cool. Thank you, Jay. So, so I'll talk a bit on the simulations, the flood simulation we did in the Bebedero Basin. In this area, in the Andes, there are several sources, flood sources. On top of heavy rainfall, it can be the frequent landslides and frequent seismic activity, but very common or documented flood source is through glacial activity, as demonstrated here in this Landsat animation. At the bottom line, what do we need to remember is in this relatively steep and partially glaciated area, rapid drainage of large water volume is very common as a flood source. In Bebedero Basin, we used HEC-RAS 2D model to reconstruct the potential flood sources and pathways, and to give general constraints regarding their magnitudes by means of volume and discharge. As you can see here in the map, the extent of the simulation was very large. And in order to complete such large simulations, we had to reduce a little bit the spatial resolution. For topography, we used the available elevation model of SRTM. A main challenge to reconstruct such floods, outburst mega floods, was to redesign their hydrographs. And we did it with documented floods from around the world, like in this work from this paper that gave this relation between volume of mega floods and their peak discharge or under different flood mechanism. Another source was documented or measured floods in Patagonia, in the Andes, that were originated from glacial activity. Okay, like you can see here, this is from southern Patagonia. Okay, so let's go into the Bebedero Basin or Desaguadero Basin. We are now looking on the upstream part of Rio Mendoza. This is the city of Mendoza, right here. Rio Mendoza goes here upstream to the Andes. And this part here, this is one of the tributaries of Rio Mendoza. It's called Rio del Plomo. Let's zoom in into its headwaters. Right here, this is Rio del Plomo. And once in a while, there's a large glacier, Grande del Nevado, that surging down valley to the valley of Rio del Plomo and forming this ephemeral lake. After a while, this lake breaches the ice dam and flooding downstream to Rio Mendoza. There are some documentation of this surging and damming in Rio del Plomo, like in these studies, and this damming resulted several floods in the last century. Some of them, or one of them, was very large, a mega flood in 1934, right here. But when we evaluated the volume of these floods, we thought that even if all the volume of these floods were drained directly into Salinas del Bebedero, it would only form a very, very shallow lake or wetland, less than 1 meter, as you can see it here. So from this, we understood that we had to simulate much larger floods that will fill Bebedero to larger depths. And this is what you see here. This is a very large simulation of very large flood in Bebedero, in Rio Mendoza, sorry. And you can see how the water flows to Rio Desaguadero. And when they flow to the south to this area, to the seal area from Bebedero, you can see that the water cannot overtop the seal and cannot fill Bebedero. Even this very large flood is the 2 order of magnitude larger than the documented flood we saw earlier. So from here, we went to simulations of the southern tributary of the Saguadero, this Rio Tunuyan. And here, even smaller simulated floods, as you can see here in this animation, were able to reach the seal, overtop it, and fill Bebedero to some extent. You also can see here that this, in the high stand of the flood, you can see some reactivation of ancient channels in a minute. Right here, these channels that nowadays are relatively dry. When we increase the magnitude of the flood in Rio Tunuyan, we see a full reactivation of these channels, and you can see how easily Rio Bebedero is being filled to a depth larger or higher than 20 meters. This reactivation of channels right here in the floodplain, this large floodplain of Rio Tunuyan, for us is another evidence for this flooding nature of Tunuyan and as a potential water source for Bebedero. To sum up this section, we saw that nowadays the recent documented floods are not sufficient not to reach or fill Bebedero. We saw that even very large floods in Rio Mendoza cannot overtop the seal and cannot be a source of Bebedero, but that the Rio Tunuyan nowadays is relatively small, but the flow distance is relatively short and is relatively steeper than the course of Rio Mendoza, can be a source, a water source for Bebedero. Of course, there is a potential that floods came from northern part of Rio de Saguadero, from this part, but as you can understand from these simulations, these floods had to be much larger than the ones you saw here in this simulation. Jay?
Yeah, and just to give everybody a sense of how big is big, how big is mega, these simulated floods here, that particularly down the Tunuyan, they're as big as the largest historic floods known, right? I think the largest historic flood is the flooding of the Indus in 1841, and so it takes really major outflows from the Andes to as you say, to fill Bebedero. I got time here. Let me just do a couple concluding slides. So, have you stopped share? Yeah, okay. All right. Just a couple concluding sort of large scale thoughts. Let's see. We've been focused in on Bebedero, but really this reminds me of this flooding of deserts is a theme that you see repeated all through the Americas, not just in South America, not just in Lake Tauca and in Bebedero, but also in North America. For those who are familiar with the region, it was host to some of the biggest mega lakes, in addition to Tauca, that are known in the last 100,000 years, in particular Lake Bonneville and Lake Lahontan, which covered the western and eastern portions of the Great Basin in Western North America. And I think it's all part of a bigger story of the hemispheric shift in climate belts, leading to flooding of deserts of the Americas peaking during Heinrich Stadia 1, because the dating on Lahontan and Bonneville, I won't present it here. And we're also working on this other place here. Here's Tucson down here, and we're working on the San Agustin. Just got some dates back on the high shore on there. Lo and behold, it's Heinrich Stadia 1. The high stand for all these systems, the hydrologic maximum is Heinrich Stadial 1. And as it is, as I already mentioned, in Bolivia, Lake Tauca, the dark blue area here between 16.4 and 14 something is the hydrologic maximum. So it's all part of a bigger picture of. I realize the causes are probably different. Some of it's glacial, some of it's rainfall, but it all has to do with more effective moisture ending up in deserts, and hence a major hydrologic perturbation. And when we talk about mega lakes, we can also talk about mega floods. The Bebedero story, it reminds me a lot of what I once heard about Lake Missoula floods, for example. There's two big floods known from North America, and they both date to Heinrich Stadial 1 in general. One of them is the breaching of the threshold at Lake Bonneville, which produced the Bonneville flood. And that spans the period 17.4 down to something like 14 Ka. So it's Heinrich Stadial 1. And that flooded out through the Snake River and out along through Washington and eventually out to the Pacific. And then the other big flood event is out of Lake Missoula in blue there in Montana. That's glacially related. And that produced the repeated Missoula floods, which also created channel scablands and so forth, famous features in North America. So you think about the flood story, not just the mega lake story in the Americas. It's Heinrich Stadial 1, and it affects both hemispheres. So I think the Argentinians were right. Salinas, I was kind of skeptical when I first went there, but I'm totally convinced now that the Salinas del Bebedero record is filled repeatedly by mega flood, well, lesser floods that I can't see because they're down in the stratigraphy. But what I have documented, and with the help of a lot, is the mega floods. Several lines of isotopic evidence point to the high Andes as the flood source. Lake Glacial was the main period of repeated flooding. Probably followed by the glacial maximum, and then finally some minor events in the late Holocene. They're less frequent and they're smaller. And they're related to, I think, glacial lake outbursts or large rains and landslides. We can't really distinguish, that are the most likely sources out of the Andes. They're truly mega floods, as Elad showed. It's on par with the largest Holocene floods known. And they're all part of this larger story of major hydrologic perturbations, the largest hydrologic perturbation in the Americas over the last 100,000 years. Glacial advances, pluvial lakes, mega floods, all relating back to increased effective moisture. All a consequence of this strong asymmetric heating, cooling of the northern hemisphere and warming of the southern hemisphere, and the shifting of climate belts. And so I'll just leave you with a thought is, so why is the chronology of the Americas so different, so apparently contrasting with the chronology of flooding in old world deserts? Let's think about your own Lake Lisan, and the chronology looks quite different. And Heinrich Stadial 1 is not a hydrologic high stand, as Adi Torstein and others have documented. And but we could also talk about the African humid phase in Africa. Why doesn't that show up in the Americas, and so forth? So I feel like I have a very tidy study coming out of the Americas, a tight story, and then every time I look at the old world, it seems like the rules have changed, or maybe I misunderstand it. So I don't know, Yehuda, maybe that's the topic of the next seminar we do when I come to Israel is this slide and this question. It really intrigues me. Anyway, I'll leave it there. And Elad, thanks a lot for joining me on this. That was great.
All right. Thank you so much, Jay and Elad, for a great talk. And yeah, we have time for questions. See that Moti unmuted himself, so. Yeah, go ahead.
Hi, Marty.
I have a question. Hi, how are you?
I'm fine, thanks. Good to see you.
You're trying to make you the answer with the bird, or you're trying to mimic me?
Sorry, I can't hear you. Would you repeat that?
No, my question was about your white bird. If you are trying to mimic Yehuda answer, because he was wearing, he just actually shaved his beard 2 days ago. Where is Yehuda? Yehuda!
Ah,
Yehuda.
yes.
Anyway, Jay, I really, I don't want to tell here a joke because I don't want to take the time, but the Israelis know the old joke about what we call Beta Histadrut. If the union of the workers is standing or not standing, you open the window and you see if the building of the union is standing or not. And I'm pointing to Heinrich, to the chronology of Heinrich Event 1. And actually, the Heinrich Event 1, of course, is not going between 18,000 years to 14,000 years, and it's not going between 17,000 years to 14,000 years. And as best as we know it, it's more or less around 16.5 to 17,000 years, something like this. So most of your flood are actually, if you believe to your ages, right? And I have a question about the ages, but if you believe to the ages, and you look on your diagram, the diagram that you showed us, the floods, most of the floods are younger than Heinrich Event 1. They are after Heinrich Event 1. That's clearly.
Some of the floods are. That's right. That's absolutely right. Some of them are bowling Alrod, and some
bring back the slide, and we look on the slide together.
Sure.
Here, you see. So most of them are actually younger than 16 or even 15,000 years. So they are after Heinrich Event 1, if we know the age of Heinrich Event 1. So you can doubt if we know the age of Heinrich Event 1, and that's another matter. So that's one point. And I think that it makes sense that they come after Heinrich Event 1. For me, it makes more sense that your floods come after Heinrich Event 1, and then actually you have no conflict with your last question of our deserts, because after Heinrich Event 1, we have a flooding period. Then I have a technical question, and my technical question is, did you measure a living shell in the waters to show the radiocarbon of the waters of this flood today, in a living shell today?
No, no, I didn't. I don't have. So I've never witnessed the flood out there. Yeah, I'd have to go up to the Andes and I guess sample it. But so it's an assumption that they're going to be equilibrium in the atmosphere, but I think it's a reasonable one.
Actually, I have some waters that I collected many years ago near Mendoza. Maybe it's too far away. And the reason that I collected this water was because Yeshu Kolodny was working on waters and teeth. And he asked me to collect river waters and to go to the dentist and collect them some teeth. And then he measured the delta O18 on them.
Going back to your comment about the age of Heinrich 1, the basis for saying that it was the age span I did is Jerry McManus's is partly Jerry McManus's record on the bottom, and you'll notice the gray swath there. It's roughly 18 down to about 14.5.
No, this is because there is no Heinrich event which is longer than about 1,500 years, almost 1,000 years. And then we know the Heinrich events from the Greenland ice cores, and we have to look on the Greenland ice cores in order to see when is the Heinrich event and what is the duration of the Heinrich event.
Well, you're right. There's a distinction between the actual iceberg release event itself and the climate impact, and particularly the impact on thermohaline circulation. And that's what that bottom one is. It's circulation. It's not ice release. And that's the climate impactor right there.
I suggest we move to the next question.
Sure.
You guys yeah, go ahead.
Hi, Jay. Thanks for the talk, and also Elad. It was great. I wanted to ask about the...
Hey, Carco, good to see you. Yeah.
I wanted to ask about the thing you mentioned last now, the climate connection.
Yeah.
So can you somehow figure out the source of the moisture? I mean, whether it's Atlantic moisture or is it Pacific moisture? Because it was hinted in your talk that it should be Atlantic or at least South American, Amazonian moisture. Mm-hmm. But I know that from recent times you can see snowfall in the high Andes east to the water divide that is coming from, for example, atmospheric rivers from the Pacific.
From the Pacific, that's right. Yeah, at this far south, you're absolutely right. The atmospheric rivers and also cutoff lows from the westerlies can reach this area. I don't think you can distinguish it isotopically. There's such a strong elevation effect in going from either the lowland on the Pacific side or the lowland on the Atlantic side, and they're coming more or less out of about the same latitude in marine sources, and they have to distill and rain out all the way up to those high elevations. I'm not aware of that. At the end of the day, it's minus 12 to minus 14 up high, and you can't distinguish the source as far as I know. I wish we could.
Yeah, because
you're right. I'm inferring that it's mostly northern sources, right?
Yeah, so the alternative hypothesis is that if you take the map that you do with the stronger westerlies and the poleward ITCZ, you can maybe change between them, but not that I have something to enforce this.
Coco, that's fair enough, and I'll tell you my bias. The reason why I think the moisture sources are tropical is the age of the high stand, the hydrologic maximum for Laguna Bebedero and for Bolivia. It's chronologically the same, and so I'm thinking, they're responding to the same event, same source of moisture, and you don't see that chronology in the lakes to the south of here. That I think are responding to the westerlies. The chronologies are different.
Okay, thanks.
Yeah.
More questions. I have a question, but I think it's for both you and Elad. So it seems that, to flood this lake, internal basin, you need to cross a sill that is only, it's several meters high, right? And I can imagine that continuous flooding and emptying of this lake can change the elevation of the sill, right? Can move sediments around. And did you test it for sensitivity? Or Elad, when you ran this analysis, this model?
Yeah,
we thought about this one for sure. Go ahead.
So it's of course a very good question. We assume that the present topography haven't changed, which of course is it's very close simplification of the situation. But yeah, we based on nowadays topography, and of course you're right. It could be that in the past this sill was lower, and smaller floods were able to go in and fill the Bebedero. Yeah.
There's another thing here, though. There's two things that have certainly changed about the topography. One is the sill elevation, and that would tend to permit possibly lesser floods from entering, as Elad's pointing out. But there's been a lot of filling of sediment in the basin itself, over 10 meters. And so it was a much deeper basin, harder to fill from the standpoint of there was just more volume, more space in it 14,000 years ago. So you got two factors working in opposite directions.
Mm-hmm. Yeah.
I'd love to do much more detailed work along the Desaguadero and along that sill. I get the sense that there's maybe 1.5 meters of sediment as you go back up toward the sill, but I haven't been on the sill itself, been close to it. That represents heightening the sill, maybe 1.5 meters, something like that. But that's not based on very detailed work.
Thanks.
Yeah.
Uli,
Go ahead.
Yeah. So Jay, first of all, thanks a lot. This is fantastic. It's always a pleasure to see new shorelines dating coming out. So I'm going to go back to Moti's comment because, first of all, the ages, right? You end up at 12.9, which means the ages are just at the end up just before the Anglo Dryas. So the ages seem good, right? And the problem is that if you think of Heinrich 1 and the Bowling Alleride versus the Antarctic cold reversal, then these two systems are totally different, right? What happens What happens after 14.6 is totally different world, right? You have warm conditions in the northern hemisphere, cold conditions in the southern hemisphere, right? So you have this bipolar seesaw which is happening in the system. So it's interesting that you're getting these results, right? And the additional problem, or the additional question is your work in Cardiel, which looks totally different, right? This time period is dry, right? And that's closer, you're closer here to Cardiel than you are to Titicaca, right? So
see, Cardiel is 49. 29. No, we're actually closer to Titicaca.
So closer to Titicaca, okay. But you're not, it's pretty close, right? You're seeing three systems now that are very different. So the question is, or not very different, they're showing something about their timing which is different. And the question is, maybe this is not telling us about a homogeneous shift. Maybe it's things like Adam Hudson is talking about in North America, where you see small scale shifts, or I don't know, Adam called it the bipolar conditions in that have to do with the positions of the westerlies and how they move through the mountains. I think that would be their interpretation. So maybe you're seeing something which is not, it's not the shift of the thermal equator, right? It's not the Broker-Chang ideas. It's something which is more dynamically driven, not thermodynamically driven. That makes sense.
Well, I think that's legitimate, and particularly at this latitude, 28 to 33 degrees south, it's on the boundary, right, between the subtropics and the westerlies, between the easterlies and the westerlies, and maybe you're right. There is more interplay of those two systems than I'm looking at here, and it's a good point that. And I can't make it go away. There is a major flood event right in the middle of the Bowling Allarod, one of the big events I see out there, that led LGE3. So it's real. And that's not consistent with what I'm saying either, as you pointed out, that Bowling Allarod ought to be sort of the opposite of a really dry period in this area. But the problem is if this is ice driven, then there's ice storage up there. And it's I think the lake, it's not just as simple as faucet on, faucet off. There's storage up in the Andes, and during a period like the Bowling Allarod, it could be just melting of ice that accumulated earlier on, and so sort of a blurring of the record. I don't really know. All of the above, I'm not sure, but both Morty and I, you point out, I really emphasize the Heinrich Stadia 1, and I'll stand by that as a hydrologic maximum. But you're absolutely right. There's all these other lesser events that appear to be associated temporally with the Younger Dryas and the Bowling Allarod. So it's yes, I agree. Probably is messier. Trying to keep it simple but I know I should never keep things simple in front of an audience like this.
Okay, I think that you guys are off the hook, and I'd like to thank you again for really a great and thought-provoking talk.
Thanks to you, Roy, for inviting me. I enjoyed this. My first time, so it's fun. Yeah.
It was fun. All right. So and we have a seminar next week. I think it's the last one for the term. So
and maybe we should ask Jay, when is he coming back?
When is he coming back? Well, Yehuda, you don't ask me. You ask my wife and your wife. Other ones that know. Well, I got another sabbatical coming up, so we'll see. Yeah.
Jay, can I ask you another question about the shouts? So why didn't you do clumped isotopes on them? Now you have because that would have possibly solved what you're looking at, right? What the source water was, at least with what the oxygen isotopes of the source water was, and you can look at evaporation, whether it is evaporated or not evaporated.
Yeah. You bet. This is right on top of my list. We've developed finally the capability to do clump isotope analysis here. And so I've been saving that question for our laser here. But as I was talking to Uli, we're like this close to actually starting to run unknowns. And this is a top choice. You're right. It would really help constrain the isotopic composition of the water much more. But still, I don't think I'm not on thin ice here in assuming formation temperatures between 12 and 25. That's pretty. We know the growth temperatures for these things, and if you do that, whichever temperature you use, you end up with really negative water. So I don't think it's going to change the story, the result, but it'll certainly tighten it. But the answer is I don't. Our laser is not quite there, and I don't want to do it anywhere else.
All right. Okay. So thank you again. Yeah, we're going to conclude this meeting.
Great to see everybody. Thanks a lot, Yehuda, everybody, Coco, Yoni. You guys, miss you guys. Take care.
Bye.
Thanks, Jake. Bye.